Let's take a look at yet another example. We again want to solve the system of equations if we can. So let's translate the system to an augmented matrix. Okay, so my first row in the matrix corresponds to the numbers in the first row in the equation. So 2, -5, 3, -2, -24 in that first equation. In the second equation, I have no x's, 2 y's, -3 z's, no w's, and 9 on the other side of the equal sign. And in the third equation, I have no x's, no y's, -3 z's, -1 w, and 1 on the other side of the equal sign. So we notice something very nice right away. We already are in row echelon form. We've got that stair-step pattern. So what we can do then is right away, we should be able to notice how many solutions we have to this system of equations. So first off, right off the bat, we can rule out the possibility of having no solutions. No solutions means we would have a row like 0, 0, 0, 0, 3. Okay? That would correspond to the equation 0 equals 3. That's no solution. We don't have that. We do, though, have a leading entry here, here, and here. One for each row corresponding for one to each useful equation that we have. But the number of variables we have 1, 2, 3, 4 variables in this system, but only 3 useful equations, which means I don't have enough equations to uniquely identify all my variables. Because of that, I am going to have infinitely many solutions. But this isn't going to be our final answer. Okay, we could do better than that. Infinitely many solutions, just saying that doesn't characterize the set of points that are solutions. And just to be clear, not all points are solutions, right? For example, the origin in 4-dimensional space would not be a solution. If I have x equal to 0 and y equal to 0 and z equals to 0 and w equals 0, then the left-hand side of this first equation would be 0, which is not equal to the right-hand side, which is -24, right? So not all points are solutions to this system, even though we have infinitely many solutions. So what we want to do is we want to somehow characterize the set of points that are solutions to this system of equations. So again, we can do that in 2 ways. We could use back substitution, or we could continue row reducing the matrix to get it in reduced row echelon form and work with it from there. All right, so again, I'll do both ways so you could see both ways. Let's start by doing back substitution. Okay. And actually, let's use the equations we already have because they already correspond to the matrix, right? So let me just take this and move it up a little bit so that I could do the back substitution here, okay? So using this as for our back substitution, we, even with the first equation here, we run into problems. This is our lowest equation, but we have too many variables. I cannot solve one equation for 2 variables. I cannot uniquely determine the 2 variables if I only have one equation. All right. So in a situation like this, that means we have a free variable. It means a variable could be anything. As a rule of thumb, your variable corresponding to a column without a leading entry, that is a good choice for a leading variable. In this case, that means variable w has a column without a leading entry in it. So we are going to let w be our free variable. Okay. So I'm going to let w equal to some other free variable t, which means I could let t be anything. Okay, so if I plug that in for w, then I could solve for z in terms of the free variable. So I have, if I solve for z, I'm going to add t divided by -3, so I get 1, -1/3, 1 plus t. Okay. Now, I could substitute that into this equation. So I get 2y minus 3 times my z, which is -1/3, 1 plus t, equals 9. So if I distribute, I get what? 2y equals 2y plus 1 plus t equals 9. So if I solve for t, I'm going to subtract the 1. It gives me 8. I'm going to subtract t. I get 8 minus t, and I'm going to divide by 2. So y equals 1/2 8 minus t. Okay? So now I have w and z and y expressed in terms of the free variable. Back substitute again. This might get a little hairy. I have 2x minus 5 times y. Y is 1/2 8 minus t. Plus 3 times z. Z is -1/3, 1 plus t. Minus 2 times w. W is t. Equals -24. So I'm going to tidy that up as best I can. And then let's bring it down here just so I have a little bit more room. So I have 2x minus 5/2 8 plus minus t minus the 3 times -1/3 cancel to give me -1 minus 1 plus t minus 2t equals -24. Now, rather than deal with the fraction, I'm going to multiply both sides of the equation by 2. That will cancel out the denominator. If I distribute the 2 on the left, I get 4x, and then 2 times -5/2 is -5, times 8 minus t. 2 times -1 is -2, 1 plus t, and 2 times -2 is -4t. And on the right-hand side, I get -48. Okay, distribute some more, combine like terms. I get 4x minus 40 plus 5t minus 2 minus 2t minus 4t equals -48. So combine my like terms on the left-hand side. I have 4x. -40 minus 2 is -42. And 5t, -2t, -4t. I'm getting -t. So I get 4x equals, I want to solve for x. I'm going to move the 42 over to the right. I'm going to move the t over to the right. So add 42 to the -48. I'm going to get -6. Add t to the right, so plus t. And divide by 4, I get x equals 1/4 t minus 6. Whew. And so I have my answer. X, Y, Z, W is equal to, so x is 1/4 t minus 6, y was 1/2 8 minus t. Z was negative 1/3 1 plus t. And W is just t. Okay. And to make it a little more obvious what we have here, I'm going to break this into a couple pieces. I'm going to distribute each fraction here. So I get 1/4 t minus 3/2. If I distribute the 1/2, I get 4 minus t over 2. Let's go 1/2 t. And if I distribute the negative 1/3, I get negative 1/3 minus 1/3 t and t. And I'm going to break this into two pieces. One vector that doesn't have any t's, so that's negative 3/2 for negative 1/3 and 0. I don't have any terms without a t there. Plus, and now the coefficients of t, plus t times 1/4 there. Here the coefficient of t is negative 1/2. Here the coefficient of t is negative 1/3. Here the coefficient of t is 1. Writing it this way, you can see that we are dealing with a line. So the intersection of whatever these are is going to give us a line in 4-dimensional space, a point on the line and a direction vector of the line. Okay? What this means is that any point on this line is a solution to our system of equations. There are infinitely many solutions. Any of the infinite number of points on this line is a solution to our system of equations. Okay? All right. So that's using back substitution. Hopefully you think that that was terrible. It's a little better, actually quite a bit better, if we first get our matrix in reduced row echelon form. Okay, so to do that, I'm going to work with each leading term, get zeros above it, and then turn the leading term into a 1. Okay, so in this case, because if I divide by negative 1/3 to turn this into a 1, it gives me some fractions. I'm actually going to get these to be 0 first. So I'm going to take row 1 plus row 3. That's my new row 3. I'm sorry, that's my new row 1. That'll give me a 0 here. And then row 2 plus negative row 1. Sorry, row 2 plus negative row 3, that's my new row 2. Okay, so I'm taking this and subtracting that to get me 0 here. So my new row 1, 0 plus 2 is 2. 0 plus negative 5 is negative 5. Negative 3 plus 3 is 0. That's the 0 that I really wanted there. And negative 1 plus negative 2 is negative 3. And 1 plus negative 24 is negative 23. Okay. Next row. Here, I'm going to take row 2 and subtract row 3. So 0 minus 0 is 0. 2 minus 0 is 2. Negative 3 minus negative 3 is 0. That's the 0 that I was looking for. 0 minus negative 1 is positive 1. 9 minus 1 is 8. And I left row 3 the same. Okay. All right, we're making progress. This leading term now has zeros above it. Let's make it a leading term of 1. So I'm going to have to multiply the row by negative 1/3. So I get 2, negative 5, 0, negative 3, negative 23. Row 1 stayed the same, as does row 2. 0, 2, 0, 1, 8. Row 3, I multiply everything by negative 1/3. That gives me 0, 0, 1, 1/3, 1/3. Okay, all right. This leading term is now a 1. It's got zeros above it. I'm ready to go to the next column over to the next leading term. The next leading term would be this one. I need zeros above that. Okay. All right. 2 unfortunately doesn't evenly go into negative 5. So what I'm going to do is I'm going to take 5 times row 2 and add it to 2 times row 1. That'll be my new row 1. Okay, so 5 times this plus 2 times that is 4. 5 times 2 is 10, plus 2 times negative 5 is negative 10. If I add those together, I get 0. That's the 0 I wanted. Okay, 0 plus 0 is 0. 5 plus negative 6 is negative 1. And 40 plus negative 46 is negative 6. The other rows stay the same. 0, 2, 0, 1, 8 for row 2. 0, 0, 1, 1/3, 1/3 for row 3. Okay, all right. We're almost there. This is a leading term. It now has zeros above it. I just need to turn this into a 1. And then this last leading term, I also need to be a 1 to get into reduced row echelon form. Okay. And so I'm going to multiply row 1 by 1/4. That's my new row 1. And row 2, I'm going to multiply by 1/2. That's my new row 2. Just so I could get those leading ones. So row 1 becomes 1, 0, 0, negative 1/4, negative 3/2. Row 2 becomes 0, 1, 0, 1/2, 4. And row 3 becomes 0, 0, 1, 1/3, 1/3. Row 3 stayed the same. Okay, this is now in reduced row echelon form. Oop, hold up. I realize I just made a mistake. You probably caught this when I did it. When I multiplied by negative 1/3 row 3 up here, this should have been a negative 1/3, right? 1 times negative 1/3 is negative 1/3. Fortunately, we didn't use that row after that operation, so the rest of the problem should be correct. Okay. Let's translate this to equation just so we see what we're dealing with. So we have x minus 1/4 w equals negative 3/2. Okay, that's row 1. Row 2 is y plus 1/2 w equals 4. Row 3 translates to the equation x plus 1/3 w equals negative 1/3. okay? So you could see we have more variables than we have equations. I have 4 variables. I only have 3 usable equations here, right? But you could also see why we chose to be, for W to be the free variable. Because once I'm in reduced row echelon form, it's real easy for me to get X, Y, and Z by itself by just moving the W term over. I could express all 3 of these variables very easily in terms of the remaining variable W, okay? Generally, your free variable is going to be the variable that doesn't have a leading entry in that column, okay? So variable X, which corresponds to the first column, it has a leading entry. Variable Y, which corresponds to the second column, it has a leading entry. Variable Z, which corresponds to the third column, has a leading entry. But variable W doesn't have a leading entry. And so it's going to be very easy for us to express X, Y, and Z in terms of that variable W. Let me show you. X is -3/2 plus 1/4 W. Just add the 1/4 W over. Y equals 4 minus 1/2 W. Z equals -1/3 minus 1/3 W. Okay, so if we let W be our free variable, W equal to some free variable T, then plug in, I have X equals -3/2 plus 1/4 T. I have Y equals 4 minus 1/2 T. And I have Z equals -1/3 minus 1/3 T. Okay, so let's put that all together for our final answer. X, Y, Z, W. So X is -3/2 plus 1/4 T. Y is 4 minus 1/2 T. Z is -1/3 minus 1/3 T. And W is just T. Give myself a little more room here. And I'm going to split that into 2 vectors. So the first vector is going to be all these components without a T. So the component without a T, the part without a T, the term without a T in the X component is -3/2. The term without a T in the Y component is 4. The term without a T in the Z component is -1/3. And the constant term in the last component is 0. Plus T times, and now we have all the coefficients of T. For X, the coefficient of T is 1/4. For Y, it's -1/2. For Z, it's -1/3. And for W, it is 1. And so again, that characterizes all possible points that solve this system of equations. All the infinite number of points, in this case, all the points along this line solve this system of equations. And we could see that it matches what we got up here. Okay, same equation, same line.